Imagine a scarce resource that can help solve global warming, enables medical imaging, and enhances national security with a price up to $20,000 per gram. And we're running out. You just imagined Helium 3. After 9/11, the Department of Homeland Security used most of the Helium 3 reserves to produce neutron detection devices, which they placed around the United States. Helium 3 is also used for nuclear fusion energy, which once commercialized can supply a sustainable and renewable energy source for all of humanity. If you inhale Helium 3, it can also be used to treat respiratory diseases, including asthma. It also enables the MRI scanner to get extremely high-resolution imagery of the lungs. It can also be used for the cooling of supercomputers, and this could also be used for the cooling of battery storage systems. On Earth, there are no natural reserves or resources of Helium 3. The way that it's produced is with tritium, which is a waste product of nuclear weapon production. There is estimated around 27 kilograms on Earth, which is not a lot. It will run out. The sun produces Helium 3 and it's transported through solar winds. Because the Earth has a magnetic field and a strong atmosphere, it repels it. The moon, however, doesn't have this, which allows the Helium 3 to be deposited into the regolith, and that has been happening for billions of years. In our process of producing Helium 3, we also produce water. As you're aware, water is required to sustain life on Earth as well as it will be in space. It is estimated that the cost to transport water from the Earth to the lunar surface is $30,000 per litre, or a quarter of a gallon. And it's also estimated that by 2030, the demand will increase to 16,000 tonnes. The mission of space industries is to extract and supply resources on the moon and provide the Earth with Helium 3 in an environmentally friendly method. In order to identify a viable and commercial resource for a commercial business model, our geologist Richard Hall has compiled an indicative resource estimation which has identified several high-grade targets for our first mission. In order to extract that resource, we have produced a lunar processing system. This includes two vehicles, of which one is an extraction vehicle and one is a processing vehicle. The resource extraction vehicle is predominantly designed to produce water and Helium 3, and in that process produces other isotopes which can be used for breathable atmosphere. The demonstration vehicle will have an extraction rate of approximately 6.5 tonnes per hour and a life cycle of 5 years with zero maintenance. The demonstration vehicle will predominantly be designed to produce water and to demonstrate the production of Helium 3. The first step for producing the resource on the lunar surface for water is to heat the regolith to 250 degrees to extract the bonded water. At 850 degrees temperature, we extract the Helium 3 as well as the other isotopes. These are then collected in the stage 1 processing system, which using temperature and pressure, we can extract the water from the Helium 3. These are then stored in the onboard storage of the lunar resource extraction vehicle. The vehicle then transports back to the lunar processing lander, where it deposits the resource into the stage 2 processing system. This system, using a membrane technology instead of cryogenics, can separate the resources into usable products. The Helium 3 is then deposited into a mineral return vehicle and extracted back to Earth for consumption there. The lunar processing lander, the first task is to land safely on the moon and deploy the resource extraction vehicle. Once this has been completed, the processing lander then becomes the resource processing and communication system. On the first mission, we're also estimating that we'll have a 1 to 3 tons of additional payload space for scientific purposes. The team that's making this possible are experts in all of their fields. We currently have 12 members, and that's rapidly expanding. My background is in mining and resources here on Earth, and we operate mostly in remote operations in Australia, as well as remote operations in the jungles of Africa. Speaking of remote operations, Sam Forbes is a remote operations specialist. He works as a general manager for Fugro in Australia, doing deep sea operations, which use high latency, similar to space. In regards to space, our advisor, Dr. Gordon Rosler, who formed Space Department for Robotics in Space for DARPA, he is now the president of Robotics in Space. We also have legal commercial space law, who is Donna Lawler, and she is well known internationally. As mentioned, we have commenced the development of our lunar resource extraction vehicle, and we have rapidly progressed with TRL 3, and we are now progressing onto TRL 4, which is our lab prototype. We are estimating to have the first lab prototype completed by Q4 2020, and the overall objective is to have a commercial resource extraction vehicle on the moon by 2024, in line with the Artemis missions. The Helium III market currently has a demand of around 100,000 litres. The problem here is that the supply to the market is restricted to 14,000 litres per year. 10,000 litres per year is for the United States market, and 4,000 litres per year to the international markets. This is because of the depletion of the reserves, and the US government has decided to build those stockpiles up again. This presents a market with no competition for 75% of that market, which is estimated at $2.4 billion annually. The other market that we can capture is the space water market. Currently, there's a demand of roughly 244 tonnes, and this is expected, as mentioned, to go to 16,000 tonnes by 2030, producing a market of roughly $160 billion with 0 competitors. Reaching 16,000 tonnes also would require 300 launches per year at 5 tonnes payload, which is more than the entire world's capability for launches at the moment. By producing Helium III and returning this to Earth, we are enabling the development of a truly sustainable and renewable energy source, which is nuclear fusion. The water that we produce in space can be used for propellants, agriculture, and also provides an efficient space transport mechanism. The water can be used to enable multi-use landers, and with the upcoming Artemis missions and a lot of infrastructure transported to and from the moon, it's much better and efficient to have a multi-use vehicle. The water can also be used to enable multi-use orbitals for thrust for the International Space Station, satellites, and the Gateway. The cost benefits are significant for refueling in space. We estimate the development of our lunar resource vehicle to be $50 million, which would enable us to supply water in space for as low as $10,000 per litre. A lander currently has a range of $30 million to $300 million as the cost. With a fuel capacity of 400 litres, would be able to be refueled for as low as $4 million. A satellite costing $50 million to $500 million with a propellant tank of 20 litres would be able to be refueled for as low as $200,000. These are significant cost benefits. Space industries are making resources in space a commercial business opportunity in line with the Artemis missions and will benefit all humanity. Thank you for listening.